As you see, she is blind. And the suitcase, she's not pulling. That case is leading her body to the podium. Okay. If you're ready, please.
Thank you.
Yeah, please go ahead.
So, good morning, and Professor Nakauchi, thank you very much for your warm introduction. My AI suitcase has just led me to the right position. But before starting, I would like to express my appreciation to the IROS 2022 organizers for giving me this wonderful opportunity to talk about my research with you here at IROS 2022. It is a great honor to be a plenary speaker today. Allow me to welcome all of you to Japan and to welcome you to this beautiful city of Kyoto. I'm very excited to share our work with you today because I need your help to make my dream come true. It has been a while since I last addressed a real audience, maybe 3 years. So I'm also very excited to present my idea directly to you instead of in front of computer screen. By the way, my name is Chieko Asakawa, and I will share a few thoughts entitled The Navigation Robot for the Visually Impaired. I will first introduce myself and share how technologies have been improving the lives of the people with disabilities, visual impairment. Then I will talk about the real-world accessibility, focusing on the AI suitcase and the progress up to now, along with new technical challenges. Finally, I want to discuss the challenges of implementing new technologies into our society. Let me introduce myself. When I was born, I was sighted. And by the time I was in junior high school, I grew to love sports. People around me thought I could become an Olympic athlete in the future. Studying was not my interest. And I never imagined that one day I might become an IBM fellow. When I was 11 years old, I hit my left eye on the side of a swimming pool. By the age of 14, I became totally blind. Soon, I found there were many things that I could do, even though I could not see. For example, sports, such as skiing, skating, running, swimming, and scuba diving. I can even rock climb.
One TBSP sugar, unused. 1 TBSP water. 1 TBSP roasted sesame seeds.
Roasted sesame. And I'm a pretty good cook. After I became blind, I found there are two obstacles for the blind. The first difficulty was gaining access to information. In those days, there were no personal computers, no internet, no smartphones. I couldn't read magazines or newspapers or any book by myself. The other difficulty was mobility. I couldn't go to school by myself. I couldn't go shopping by myself. I couldn't go anywhere by myself. I really wanted to be free from relying on someone. I wanted to be independent. That became my strong need and pushed me and ignited me toward invention and innovation. After many twists and turns, I joined IBM Research in 1985 and started working on accessibility. I then happily discovered that IBM has a long history of accessibility. Back in 1914, IBM hired its first employee with a disability. that was remarkably early, long before society began paying attention to such issues. In the 60s, IBM developed a talking typewriter shown in the slide. In the 80s, a talking terminal was developed. You can see me using that terminal in those days. In the mid-90s, I was able to access the web in the lab within a special environment. I was astonished because I could read a newspaper at any time and every day. I could search for any information by myself. I desperately wanted to help all blind and visually impaired people to have access to the web. I found a different way to render a homepage so that instead of using a computer screen, it used a synthesized voice. And for a mouse, we instead used a number pad. That dramatically simplified and made easier my own user experience. It led me to develop the IBM Homepage Reader or HPR in 1997, first in Japanese and later translated into 11 languages. The HPR paper was published in 1997 at ACM Assets, and the paper received the Long-Term Impact Award from SIG Access in 2013. When the HPR became available, we received many comments from users. One I strongly remember said, HPR is a window to the world. The internet offers a completely new type of information resource for people with visual impairments. Okay, here is a snapshot of my home screen of my smartphone. Now, smartphones offer a new experiences to the blind, to access information, to interact with others, and to operate a host of appliances anytime and anywhere. Other examples are online meetings, online banking, online shopping, booking hotels and flights, accessing dictionary, listening to music, podcast, finding favorite restaurants, communicate via SNS, and of course, emails, phone calls, and many more. For accessibility apps, recognizing objects and characters, reading text, checking barcodes, finding ways and destinations, the number of variations and options are increasing. And our lives, those without vision, are getting more and more convenient. Let me share a story. When the smartphone was becoming available around 2010, I thought, no, it is impossible for me to use it. I didn't want to use it. I wanted to stick into a featured phone because it was much easier to make a phone call. I defied progress. Wow, was I wrong? Now, I cannot conceive of my life without a smartphone, just like the rest of the world. Nowadays, my research focus is on the real world. Currently, while walking in a city, I cannot recognize shops around me, items in the shop, if there is a long line, or if my friend is approaching. I am unable to perceive these visual information without technology. That is my research challenge today. This video shows my exact goal. Please watch it.
That is the flying eyeball. Chieko, do you know what it is?
It can't be identified. Maybe a kind of monster. Beware of it. It's too dangerous.
It is a very, very old Japanese TV program for kids. I liked it when I was a child and could still watch it. The little bird on the boy's shoulder is a robot named Chieko. Chieko helps the boy by whispering to him about everything around him, from the weather to approaching enemies. It was a science fiction in those days. But now we have AI, robotics, and a variety of sensors. I decided the time had come to bring this science fiction to life. Technology like this could be notify me of crossing streets, traffic lights, bicycles on the street, stairs, escalators, elevators, any information that allows us to walk independently. Even more, it could help me navigate and avoid collisions, wait in lines at a coffee shop, describe scenes and people's behavior in the real world. The idea for the AI suitcase came from my own personal. I often travel alone with a suitcase. Sometimes carrying a suitcase and a white can at the airport is too much. So I found a technique to use a suitcase as an alternative white can. You can see it in this video. I think now you know what I mean. I thought if AI perception, planning, and control could be integrated into a suitcase, it could be my new travel companion and help make my travel life much easier. To develop an AI suitcase, we needed to combine various technologies. For example, perception technology to avoid obstacles, control technology to move smoothly in a crowded place, tactile or haptic technology, audio interface for notifying the user of the surroundings, and the basic hardware technology of a motor, batteries, and so on. These technologies are essential, and we needed to collaborate across different organizations to bring all that together. So we started the AI Suitcase Consortium in 2020 to develop practical robots and accelerate social implementation. Alps Alpine, Omron, and Shimizu Corporation are working with IBM. The Japan Guide Dog Association is providing advice from the perspective that the robot can be a new option for the visually impaired. Carnegie Mellon University is still leading development. Waseda University and Keio University are working on related research. ACE is a Japanese suitcase company. They provide suitcases for the latest version. Plus, Miraikan recently became involved. Please take a look at this video.
Going to a sweets shop. Approaching automatic door. Push the elevator button on your right. The elevator is opening. Getting off the elevator. You have arrived at the sweets shop. Going to Mitsukoshi Mai Station. Avoiding a person. You have arrived at Mitsukoshi Mai Station.
Okay, so I would say our project has developed to be our 11 or 12-year-old child after several years of efforts. This slide shows the history. 2018, our first AI suitcase at the CMU. It was enough to share our ideas. 2019, the suitcase is smaller. In 2020, finally, in collaboration with Globetrotter, a suitcase company, we made a nice-looking suitcase robot. I liked it very much, and we call it the GT model. This year, we developed two versions. One is at Miraikan, an upgraded version of GT, so we call it the GTM model. It is being tested at Miraikan to increase accessibility for a museum experience. Another is by the consortium. It is targeted to be more practical and sustainable. A Japanese suitcase company, ACE, has offered their suitcases, so we call it the ACE model. I used the ACE model to walk to the podium today. We've been experimenting with it at a shopping mall in Tokyo by inviting blind users to try it out and give us feedback. It is a carry-on baggage size. We can select a destination by using a smartphone app. It searches for the best route based on a pre-registered map and the current location. Then it navigates a user by avoiding collisions with pedestrians and obstacles. The robot is equipped with various sensors. So, as you know, this is a LiDAR. A LiDAR on top of the suitcase measures the distance to the surrounding wall and obstacles, a 360-degree perspective, and the robot estimates an accurate location inside the building. 3 RGB depth camera under the LiDAR are used for detecting pedestrians. There are left, right, and front. Now I'm open the suitcase. Okay, so an embedded GPU cluster, backside of the fan, does image analysis, and a computer on the left side does localization, controls maps, communicate with a smartphone, and manages the user interface. Under the computer, there are 2 motors that support walking speed and power to handle bumps and tactile paving. So we chose a higher gear ratio, 1:2, so a user can push manually the robot suitcase just like a regular suitcase. This is necessary when going through doors. And above the computer is a microcomputer that controls sensors embedded on the handle. It's very high. So the 3 vibration devices are top, left, and right side of the handle to present the turning direction and the starting notification. For example, when turning right, the right side vibrates, so a user will be ready for the right turn without being notified in audio. In this way, it can divide necessary information to be conveyed either through audio or touch. And when you hold the handle, it starts moving. And when you let go of the handle, it stops moving. And the speed can be controlled by pressing buttons on the top of the handle here. And the walking speed can be set from 0 to 1 meter or 0 to 3 feet per second. And battery here. So there are enough batteries to operate all devices for about 3 hours. Okay. So we have spent time while using a commercial suitcase. So we can confirm if our idea of the suitcase-shaped robot is doable. Okay, so we received significant positive feedback from end users. Like, I feel independence that I've never experienced after I became blind. I want to bring this robot back to my home. I really like this one. I want to give the robot a name like my guide dog. And another memorial comment was, I feel comfortable walking seamlessly and naturally in city areas without being recognized as a blind person. I don't feel like people are watching me because I walk confidently. However, some users commented, it might be a bit scary because passerbys do not notice we are blind, and we may not expect necessary help. They questioned, should we carry a white cane even if we don't need it, just to be recognized? When visually impaired people walk with a white cane, they often risk going the wrong way or hitting an obstacle. So they sometimes need help from surrounding people. A Japanese road traffic law requires the visually impaired to carry a white cane or to be with a guide dog when they walk public spaces. But the AI suitcase is much better in that it will not go the wrong way or will not collide with an obstacle. It can easily navigate a user to a destination. So the visually impaired do not have to carry a white cane. They will be able to walk around public spaces without drawing unnecessary attention from people. In our survey, on the other hand, we often hear that it is impossible to support a visually impaired person if they are not visually noticeable. Yet, the current law requires a person to carry a white cane, as I mentioned. What do you think? Invention and implementation are a pair of wheels for concept. A great invention cannot change our quality of life if real users don't use them or if they are not implemented into our society. This is especially true for an autonomous robot like the AI suitcase. We face a number of challenges to bring the suitcase to the market. Let's look at 4 challenges: technical, acceptance, business, and infrastructure. And I want to share our efforts to overcome them. When we target a city-wide area, it means we should go well beyond a laboratory scale and step into the wild. That is why we selected this experimental field. There are 5 buildings totaling 31,360 square meters, in addition to the 300-meter corridor. To cover such a massive area, we first improved the pedestrian avoiding capability of the robot. And we also improved it to be capable of rider map switching to cover a wide area, all with a limited memory footprint. Please watch the video.
Approaching automatic door.
Among stakeholders, the most important collaborators were and are the users. They must live with what we create. So their feedback is reality. So from August to October 2022, we successfully conducted a series of pilot sessions with 40 blind participants, 1 hour each. Please take a look at the video. As mentioned, we received quite a bit of positive feedback from users, but they commented if a robot avoids pedestrians more smoothly, it would be great. We have been working to predict pedestrian behavior so that the robot can take action earlier, whether it should go straight or avoid collisions based on the prediction. Another expansion is to the outdoor. Not only just cover the outdoor environment, but the robot should also move seamlessly between outdoor and indoor environments to handle scenarios like going from a train station to a stadium. We integrated an outdoor localization system, RTK-GNSS, with LiDAR-based localization. RTK, real-time kinematics, is highly accurate method to calculate the position of a rover at centimeter level by using correction data transmitted from a base station at a known location. The picture shows an AI suitcase with RTK GNSS capability. Thanks to the small footprint of the multi-band antenna, the improvement does not impact the robot's design. Please watch the video.
Going to IBM reception. Automatic door approaching. Entering the IBM building. You have arrived at IBM reception.
Okay, so 3 types of maps should be created in advance to operate an AI suitcase. The first map is a LiDAR map for localization. We need to scan the entire area and create a 3D model of the environment that includes walls and obstacles. The second map is the topological route map for navigation, and the third map is the point of interest information that allows them to learn and enjoy the city environment, like shops, restaurants, and as well as any other facilities like automated doors and restrooms. Without these 3 maps, the robot cannot be used in an area. This preparation takes time, and it is not realistic to create a map for all public buildings in any city. This is one of the critical limitations for the area expansion. One of the solutions we are studying is mapless navigation. If a blind user can just bring an AI suitcase to a public space and then alone train the robot to move in the public space, it could be a game changer. And now we are focusing on intersection detection and selection-based exploration as the first steps. To detect an intersection, we first create a map using LiDAR SLAM and analyze the coast map image. Our algorithm can then generate a topological route with a detected intersection. A user can explore the environment by turn-by-turn navigation using the handle interface. The AI suitcase stops at each intersection, and the user can select orientation by using the right or left button to decide the route.
Going to the next intersection. Found route to left in front. Turning left. Going to the next intersection. Found route to left and right. Turning right. Going to the next intersection.
The current prototype has various limitations. Glass walls, for example, are difficult to detect using the current algorithm. I'm sure you can imagine the challenge. We have a long way to go to make the mapless navigation workable, but we see great possibilities in overcoming them. Even if we successfully advance and evolve the technology, technologies should be accepted by society. I mean that by the general surrounding public, who may work side by side with the robot and user. We have recently experienced and expected to experience various social acceptance challenges in the accessibility field. Smart glasses would be very useful for visually impaired people because they can help them understand the surrounding world. But sometimes people don't like them in public spaces because due to the privacy concerns. Safety is also another important topic that requires societal understanding. Take the case of the autonomous driving vehicle. Even if autonomous vehicles become completely autonomous, like level 5, do people accept if a visually impaired person or a child, neither with a driver's license, drive the car? We always must explain the progress of the technology. We need to explain how safe the technology is. We need to we need to keep communicating with society for mutual understanding. We do have a few bits of good news. Based on the latest research, people understand the importance using new technologies to augment those that have missing or weaker abilities. Kyujun studied the social acceptance of wearable camera devices. People have negative feelings about using them in public spaces, but feel significantly positive if the device is operated by a blind person as assistive technology. The first question from facility managers when we discussed the possibility of a pilot program was acceptance by society. How do they feel? Scared? Comfortable? And can we reduce such friction by seamless robot movements with the surrounding people? This slide shows one of our research results. We asked 300 people via a crowdsourcing site. We found they feel more comfortable with a robot accompanied by a blind user compared to a robot without a user. The use of such suitcases can be a door opener for technology to be understood by society and accelerate the implementation of those new technologies into society. Okay, so if consider social implementation, we must also consider mentioning the business challenges. The AI suitcase targets blind people, so the market size is significantly smaller than the general population. But if we see the blind population in the world, it is 36 million. Not that small, right? We can imagine the future impact and the growth opportunity by targeting that global niche market. And if we can expand the technology to cover the elderly population as well, like AI senior workers, the population expands by another 30 million just in Japan. It is another growth opportunity. The cost is another side of the equation. The prices of major components like LiDAR, a battery, a motor, and a GPU are all decreasing in the long term. We can expect a constant reduction of cost in the next several years, along with the penetration of related devices like autonomous vehicles, drones, delivery robots, and so on. For the autonomous robot era, our infrastructure should be improved. For example, every pedestrian needs to follow the signal to cross a road. Yet, robots can see a signal and its color, but may misread it. If a signal color can be accessed via the internet or via a radio wave signal, like Bluetooth, it would be much safer to cross busy streets for everyone. However, at this moment, there is no standard and no implementation plan for such infrastructure. But for autonomous cars, the ITS, Intelligent Transportation System standards, are defined on a global scale. Another infrastructure challenge is elevators. Most of the robots cannot push buttons if a robot could call an elevator via a network API, it would be seamless and usable, not only for AI Suitcase users, but also people with hand motor disability and other people who have difficulties pushing the button. Okay, so everyone at this conference believes that soon many more robots will be moving around us, right? Yet, as mentioned, there are many challenges. The AI Suitcase shares these challenges, especially for acceptance and infrastructure challenges with other autonomous service robots, like delivery robots. A delivery robot needs to move through pedestrian crossings and to call an elevator. People need to accept such an autonomous robot operating around them. So any service robot may have exactly the same challenge as the AI Suitcase. I believe the AI Suitcase can be a vanguard for implementation in our city areas. Robots assisting persons with disabilities can be better accepted than general unattended robot, as I mentioned. When we look back at the history of technology, we see many cases where the special needs of people with disabilities motivated engineers to invent new technologies. The telephone is an example. In the 1800s, Alexander Graham Bell invented the telephone. Why? His mother had hearing impairments, so he became interested in acoustic engineering, taught himself, and invented various technologies. He also established a school for people with hearing impairments. Through these experiences, he invented the telephone in 1876. The first opportunity to show the invention was the Philadelphia Expo in that year. He actually wanted to show it after refinement, but his wife with hearing impairments forced him to put it on display. The demo was praised by the judges and awarded the gold medal. It led to the rapid spread of the telephone. The very next year, 1877, the Bell Telephone Company was founded that later became AT&T Corporation. Very quickly, other telephone companies were founded all over the country. This is not a one-time phenomenon. We have seen this repeatedly in our history of technology. You can imagine how the speech-based interface was motivated by the needs of people with disabilities. Accessibility needs nurtured voice synthesis and voice recognition technologies to be the mainstream and proved the importance of these technologies in our society. The next big thing is, of course, AI and robots. Accessibility could be a flagship case for cutting-edge AI and robotics, and accelerate social implementation by clearly showing how such innovation has the power to change quality of life. I strongly believe it will lead us to the next generation of breakthrough invention. We have a major opportunity at the Expo 2025 Osaka in the Kansai area. One of the goals of this expo is the Future Society Showcase. The expo aims to give a realistic picture of future society by applying advanced technologies. In 1876, the expo accelerated to the implementation of the telephone. In 2025, we hope the Osaka Expo will accelerate the implementation of next-generation assistive robot technologies. I've had another role since April last year as the head of the National Museum of Emerging Science Technology, nicknamed Miraikan. Mirai means future in Japanese, so it can be translated as Museum of the Future. It is known for its focus on the frontiers of science. You can see some beautiful picture on the slide. Miraikan could be a future miniature city with a restaurant, cafe, shop, theater, classrooms, and many futuristic exhibitions. I believe such a place can be an experimental field for new technologies and innovation. Kids, the elderly, people with disability, each visitor experience the new technologies and innovations, which may change their daily lives in the near future. In this way, we can expect to accelerate social implementation. This year, we launched the Accessibility Lab Consortium at Miraikan. The lab serves as a hub that brings experts from companies and academia to work together to invent new accessibility technologies. Then pilot test them at Miraikan with visitors with or without disabilities toward implementation. I hope to make Miraikan a role model as a world-class example of an accessible museum. We welcome all related researchers who are interested in working with us and with visitors. We also welcome you to stop by on the way back to your country. And remember, we close on Tuesday. We believe the navigation robot for the blind will make blind users independent and dramatically improve their quality of life. There are many implementation challenges, but we believe the needs of the blind population will open the door to a future with assistive robots. This is my dream. To bring such a future closer, we need an experimental field to pilot and experience technologies. We call such an environment the cityscape of the future. Expo will be the cityscape of the future in 2025, and Miraikan will be a cityscape as a long-lasting experimental field. And we would love for you to be involved. Let's all work together to create our future. Thank you very much.
Thank you, Chieko.
It is really a splendid talk. I personally see this is a really user-centered and design and development, and you are very precisely thinking about social implementation of your proposal system. Thank you very much, and I would like to take short questions to her. Okay, please go ahead.
Great presentation. I just had a question on the, could you elaborate on the door detection or the elevator detection?
You mean that if we do the door detection of the elevator?
Yeah, like.
Yes, yes. We try to detect the elevator door, but we have a map, as I mentioned. So map helps better detection.
So it doesn't like detect the doors itself, it just finds the area on the map that has a door? Or?
We know there is a door near there, but we do the door detection as well. We use both.
Okay, all right, thank you.
Okay, second people, yeah, second, yes, please go ahead.
Thank you for wonderful work and inspiring talk. I have a question about the acceptance from the visually impaired people. As in, there is the two type of people who use the white cane and the other use the guide dog. What is the notable difference in accepting this navigating assistance system?
Okay, so you mean the differences between a white cane user and a guide dog user?
Yes.
From the acceptance perspective, right?
Yeah.
Okay, so, a guide dog, so it's going to be a long story because we have been studying the difference between guide dog and this kind of robot. And so guide dog user, for the case of guide dog user, they cannot have a guide dog with them if they started using the robot. So, but white cane users, they can keep both of them, a robot and a white cane. So that is very different from user's perspective. So, but still, a guide dog never knows the destination. Always a user has to tell a guide dog where to turn, where to go. So, it's a kind of mixture.
Yeah.
So, but, carrying a white cane and walk with a guide dog is really different.
Yes. Thank you.
Okay, please, quick questions. He's the last. Okay, sorry.
So in terms of the design for the robot, have you looked at different means of locomotion? So with the age of Boston Dynamics, like dog robot, you could see an equivalent, like maybe you could have a guide robot with that could navigate stairs, gravel, curbs, but maybe there is still value in having a traditional suitcase in that it's discrete and it's familiar as a design pattern. Is that something that valuable that blind people would gear to in terms of what choice of robot they want?
Yes, so it's a good question. So of course, the first idea came to our mind should be, let's develop a guide dog robot. Because, dog can go upstairs, downstairs, but the suitcase cannot, so we have to carry. So it has to be very light. But, we have studied the past, related work, and there are a few guide dog robot challenges. But, from the practical point of view, it still takes time. So it's going to be very heavy, and some users don't want to have a big robot with them. So smaller and nice looking and natural were our first priority. But of course, I understand components and sensors are getting smaller and smaller, and material is going to be lighter. So I'm sure at some point we can, look at the guide dog robot again. I mean, for me. So For me, right now, we focus on lighter and carryable robot.
Thank you so much.
Thank you so much.